we began our first session from Dr. Osama, Professor Osama Mohamed from USA, Florida International University, Miami. Under his paper, under the title, Operational Security and Control Challenges in Smart Energy Systems. Would you please give us the honor of giving out your speech? Thank you.
Thank you. Assalamu alaikum. We'll talk about operational security and control challenges in smart energy systems. So this presentation will be a bit heavy on the type of cybersecurity and also control of power systems. This is an overview of what I'm going to say. We'll talk about the smart grid communication and control challenges. Although the term communication actually, sets some fear in some researchers, which we, as power system engineers, we don't really know much about communication. But it's not as difficult as you think. So we'll talk also about the cyber physical system for smart grid infrastructure and the threats of hardware, software activities that happen in the system. Also, security-aware power system design. When we design power system components, we design them for power system operation. But if we're going to be designing a component to also identify if there is any cyber attack or if there is any malware that has been introduced into the system, we need that component to identify that there is something wrong happening here. Then applications in cyber physical system design, in terms of validation and test cases, we do it on a smart grid testbed in our university. And one of the reasons we do this is because when you develop techniques and you go to power companies and ask them to test something that you developed in the lab, they definitely don't allow you to do that because they are connected to customers and they don't want to do anything. So you have to develop a test bed with hardware and software. Then we talk about cybersecurity solutions for energy systems, incorporate the security and design of the microgrid, and also what about using energy storage to mitigate cyber attack in terms of denial of service, and also look at the AI and machine learning kind of activities to detect the anomalies that happens in the power system and the multi-agent classifiers for cybersecurity. For smart grid communication challenges is the term interoperability. How devices that are built according to different protocols, how do they communicate with each other, how would they know? That would be definitely in the software layer. Next is to identify the communication network and the bandwidth that is required to measure and collect the data from remote sites. That is definitely for distributed control. And data availability. So when you need information coming from another device, if it is delayed, corrupted, or there is an attacker that caused a denial of service attack, you need to identify these, and then the data security and privacy. This diagram here shows the different layers of power system operation. Down at the bottom is what we call the customer network or the home area network. Down here is where we have the homes with the microgrids, and if there's an EV park, or if there's energy storage and renewables and so on, and then also energy management systems and battery management systems and so on. And then the next layer up is the neighbor area network. And from the neighbor area network, you go to the field area network. And the combination of all of these items go to the upper layers, which we call actually is the for the residential control, substation automation. This is the wide area network that we control, and then this is definitely connected to the control center. Once we do this for the area for the control center, control can be distributed definitely has to be distributed, or it can be in bulk, which I'm going to talk about the differences here between these. Power grid cybersecurity attack risks, it is very, very vulnerable to cyber attacks. For example, around the world, power grid actually does have quite a large number of the total percentage of the cyber attacks that happen on critical infrastructure, whether it is water systems, nuclear power plants, government facilities, and healthcare industry, and so on. So it followed a 28% increase over the past many years. It is so important in the United States and many other countries that critical infrastructure protection, or we call it SIP, this is set by U.S. presidential directives, simply because of the seriousness of the matter, and whether it is a ransomware attack or any type of attack that stops the energy from going to customers. So this is since around 2013, most utility companies are controlled by a SIP and the NERC, which is the Northeast Electric Reliability Corporation. And failure to do that, so many of the companies will be subjected to fines, major fines as a matter of fact, to be able to do that. So more about the monitoring and the security threats for the power system. Most of the protocols that were developed for more efficient data transmission, that was done without considering the security requirement. So most of the relays, ABB relays or GE or Schweitzer or some of those companies, they typically built them with data transfer but without really taking security into them. Just recently this has started to get into the realm of actually including the security awareness in the system. Physical measurements units, BMU, depend on external clock source, which can be spoofed or jammed by attackers. And the PMU protocol, which is the C3718 or IEEE 1334, that does not support the authentication. So if you look in these diagrams here, it shows the control center and the state estimator. I have an example I'll show in a minute with all the information and the data. When the data moves from one device to the other, it moves according to a protocol. And that protocol can be exploited by the attacker. This is a wide area monitoring thread, and I think it's an animation. I will show you here, for example, where a state estimator can detect data from faulty meters. For example, if we have bad data from a faulty meter, and this bad data passes through the state estimator, and it does, we do a bad data test, and if the bad data test does not pick up, so it becomes a bad data, so error will be identified. So sometimes there is no stealth attack that happened right at the communication network yet, but a stealth attack can happen at the communication network area. So that data is identified. So this is the correct case, or this is the good case. If the communication infrastructure is able to detect the attack, then that's the case. But on the other hand, if we have a state estimator stealth attack, which is an attacker would write a code, eavesdropping on the information transfer between components, and that actually passes through the state estimator, and if it doesn't pass the data test, then it goes through a correct data, gets identified as correct data, and it moves, and the bad data not identified. And so in this particular case, the system is under attack. So for wide area monitoring security measures, the design, the security aware wide area monitoring system, we have different factors, and it's data authentication. What that means, it means we want to ensure the source of the data, where it's coming from. Do I respect or do I trust this data or not? And integrity, which is the data has some corrupted strings or some corrupted information, or when we change data, and also proper location of highly secured and encrypted meters, some special components located throughout the system, mainly meant to prevent state estimator attack. And we can utilize data mining techniques to detect altered data. So there are many techniques available that we can test those data. For substation automation threats, many of these IEDs, this is intelligent electronic devices. What that is, it's the relay or another device in the system or the intelligent controller. It can be, so all of them do operate based on certain protocols. The first protocol is the manufacturing message service, MMS, or GOOS, object-oriented substation events. ABB relays, for example, operate on this. And then the sample measured value data, or SMV. So these are the different types of protocols. And typically it becomes important when you are on an Ethernet process bus that you have an ability to translate these protocols. So all of them can be understood by other devices that are actually operating by another protocol. The IEC 61850 is a major protocol that is a new international standard for communication, which enables the integration of substation functions, protection, control, measurement, and monitoring, and so on. These are all done to identify the various aspects that happen. For example, what is the abstracted data actually represent? So all this abstracted data that you see on this slide here can be identified as logical nodes for a circuit breaker or device bay controller. So how would you communicate between the different devices in one bay? And also the data element to identify whether the switch is open or closed. You need to identify that, and then the device logical relay, which can actually have the controls between the dotted box in the middle there. So these are all data that's in the back of the relay, and they represent the abstracted data. So for substation automation threats, we have the GOOS messages, and we have the SMV. So that will be more related to manipulating of the control commands and maliciously open and close breakers. So if I can eavesdrop on the information that is coming out of one relay, and then change the message that say open and then make it close, or I change the timestamp, or I change some other factor in communication, then I can actually create a brownout or a blackout if that happens. And for sample value, they manipulate the current and voltage values, which actually lead to false state estimation, as well as tempering of the status of the circuit breakers. So that can be a major problem as well. The boost manipulation, what we have tried in our lab, and then actually this is really the process, how would you change something that happens in one of the IEDs, intelligent electronic devices here. So the publishing IED, it sends information to subscribing IED, okay? Now, in the middle, there, if an attacker can listen to the information and then capture it, you can easily write a small code, take this data, and then actually change it physically. And then, in that case, the subscribing IED will not receive the correct data. So this is the data can be altered down in the red box there, and it can go back to the subscribing IEDs as an attack type of component. Okay, exactly that's what happens here. So, for example, in the red boxes here, you see status number 2. In the green boxes, shows status number 3. And in the blue boxes, status number 2. Easily in a code, because you have this, and then you are eavesdropping on the data, and then this data you see it as a stream on your screen, you can definitely just go ahead and change that. And then that's what will go into the the other side. So you can change the status number, you can change the timestamp if you can. So we can do a boost manipulation in that way. With SMV manipulation, what can happen for hardware implementation example here, we have to receive the data bus and from model and then save in the coefficient. And then what we can do here is to look at the data that's coming out of each one of these in terms of voltages and currents. Okay? So what you can see down here, you can take the measurements and then add it right into the data that's already given by the SMV protocols. So you can definitely put in fake measurements. Okay, like you can see it here. So this can easily happen in terms of the SMV numbers. So the idea here is now how to be able to find those types of manipulations or those types of changes that will prevent a cyber attack from happening. We'll move a little bit into the control, and as you can see here, we have a controller, the red box. That's a controller, centralized controller. Like the power system in the past was operating a centralized controller. If there is a failure in a controller, all the subsystems that are connected to it will be in the line. Okay? So the cyber physical security should not only be considered for the cyber components, but also can be considered for the control. But what do we do about this? What we do about this is to try to create a security-aware distributed control system. So if we break, instead of one single point of failure, we can have multiple points of failure. So the advent of having blackouts is going to be a little bit less in this particular case, but nonetheless, it is still decentralized, but not fully centralized. What we need is something like this, which we call completely distributed multi-agent type of network. And the idea that we want to be able to do that, every controller or point that you see here is actually having information or being able to see what the other controllers are doing. So we implement this with agents, and then the agents will communicate with each other, and they will tell the other controller what is happening around them and all this stuff. So in other words, we need to increase the data between all of these computers. So attack detection can be improved by data mining, and this would be something that will be implemented as multi-agent control. For co-design of security-aware power system, number one is the type and levels of data protection should be coordinated with the signal sensitivity. And also the attack detection should rely on the physical system characteristics as well as cyber rules. So there are many attackers that study the physics of the system very, very well, such that their attacker or the code can predict what is going to happen from a physical point of view. It can happen. How will you be able to do that? And then attack countermeasures should be considered in the dynamics of the special system parcel. The way we implemented this in our lab is that we encourage the student to actually try to create a cyber attack, and other students try to determine how they can stop it. So typically, we create the attacks, but then we need to find a way to actually implement how it can be stopped. Okay, the simulation and design tools for smart grid. We need new modeling techniques. We need also a facility test bed, because utility companies will not really allow you to test something on a live system. So the only way we can do it is to actually develop a system that is actually close to a live system, and test things on it, for terms of communication, software, as well as physical components. And then the simulation tools in the test bed can also be implemented as well. So cyber-physical infrastructure environment is required to identify the possible vulnerabilities, and test environment should seamlessly integrate the different protocols. So our test bed that we have here has these following capabilities. It actually has commercial components, phasor measurements, distributed renewable energies, and new operational schemes, intelligent protection schemes, and also emulation, plug-in hybrid electric vehicle. It also has integration of hybrid AC/DC systems, as well as cyber infrastructure in terms of communication network. So there are multiple layers in that system. This is actually the various modules that included in this test bed. We have multiple microgrids here on this side, connected to the main grid through multiple DC buses, through a DC grid end, was bidirectional converter. So we can move energy from microgrids to the AC side, and from AC side to the DC side as well. So this is an actual picture of the test bed, how it's happening here. These are some of the Egyptian students that are actually working on in the test bed. And it has hardware, software, communication layers, and the project-based sort of educational activities that happen in this. So we try to teach the students how to actually build these components and then build capabilities into these activities. This is the back side of the test bed, which has the microgrids and the monitoring, control, and protection and communication. The sizable laboratory scale is actually 120 kilowatts, which is big enough to have a sizable sort of a testing capability. This is how the connectivity that occurs between the different components in the system for the microgrids through the wide area control infrastructure and wide area system, and also the wide area protection system that occurs in the system. So we have implemented all the different types of protocols for also protection infrastructure as well. This is the various layers that we have in this bed. So at the various types of areas here, we develop on these boxes here, which represents a circuit breaker with a circuit breaker agent with embedded platform. So we can embed the solution and have that continue in that fashion. So these are the layers of how we break up the system. So we start with a configurable transmission network. In other words, we have bus modules, hardware-based bus modules, hardware-based line modules. So this system, once you create the architecture, then it becomes the power layer. Okay? Next, you will have a remote control of circuit breakers. You will have another load agents added for embedded platforms. And then you have generator and the prime mover control for distributed generation agents for embedded controllers. And then we have hybrid microgrids that can connect to the system. And then this DC microgrid that can connect. So hybrid means that we have something that is AC, could be a wind and solar and so on. And then this one here is a DC microgrid. And we have control and communication that is available in every one of those areas. And we have a communication protocol that is essentially embedded in these multi-agent type controllers. So the controllers are embedded on to the agents that you see there. Okay, so this is an example of the logical structure of the distributed agents and their interactions. So this has an animation now. Once it started, it will tell you. So the agent configuration and parameter initialization. So the agents are initialized. So the system starts by initializing all the components, as you can see here, and then it sends the information to the various parts, and then it identifies it's ready. and then the agents are initialized or configured. So the load agents send a demand signal. I need a certain amount of power, okay? And then that information, whether the DC, DG, and energy storage agents does that, and then the microgrid agents exchange the information and transfer the data from the base to the server. And the social behavior is also determined, so we have software that's added here to plan and identify the social behavior, and especially if we wanted to do some kind of consumer activity, for example, like market creation, so we can create a market where we can decide whether we're going to use this information or not, and then it sends back everything to the power DG agents, and then after that it stops. So you can run a scenario of the overall system with this. Also at FIU, we do have a commercial level 1.4 megawatt solar system. It's in the back of the building. It is actually connected to the utility company. So the utility company put it there to help improve frequency response in the region. And there's also a 1.2 megawatt battery facility on the other side of the building that this also charges the battery, and then the batteries can connect, actually connect to our building in case of emergency. Okay, so the communication middleware is something that is needed really for achieving this type of operation. So this is the type of embedded controller, and then this is the communication network. So this is the network, the hardware, the operating system, the communication middleware, and the control logic, as well as the control application. So the communication middleware should be either message-centric or data-centric. So I'll talk a little bit about that. The idea here is that either you choose data-centric or message-centric is how much time it essentially takes to change information or to execute information. So in the application layer, we do all these applications. As you can see here, the message parsing, the data filtering, the data and state management, and so on, and then the network is alone. But if we do, we want it improved operation, then we can have the middleware, such as DDS or OPC kind of middleware. So this is another protocol that is actually need to be used, where the information, all that information is done actually by the middleware. So you don't have to really perform too much functions on the application layer itself. So it does take a little bit less time. So you are able to do that filtering in the middleware. One thing else that I want to tell you, that if we combine, if we look at the differences between message-centric and data-centric, so these are the efforts that actually moves to the communication network, and it's calculated by the, so these are the efforts that are saved by the data-centric middleware that we can have here. So the idea here is that how do we do this fast? How do we do it seamlessly without much change? So the data-centric chosen to be used for the smart grid display as well. So this one also emphasized by industry. The smart grid interoperability panel, widely available on the web. You can see some of their protocols that actually utilize this type of data. For data distribution service is actually pretty much common in industry, and it essentially becomes a platform where you can connect many different hardware components that actually can be understood by each other. So data translation per se. So the IEC 6150 implements real-time publish subscribe. So if you want to publish information on the web, then before you are able to use it, you got to subscribe to it. Okay? So during that process, all kinds of things can happen. And one of them is data distribution, service middleware, live service versus publish subscribe. So you want to avoid something like this on the left. transmitting the data. Like you see here, it goes from here to here. But if you have a failure in the communication, then nothing is going to happen, right? But if you go here in the transmitting nodes with the DDS data bus, then you will actually you will continue to have the information. So the transmitting nodes and the receiving nodes are on the data bus. Even though from each one of the blue or each one of the green could be different protocols. The data bus can have the ability to make a protocol translation for this. So there is a big reliability here. There is a high update rate, and also it is low latency. Also, for data distribution service communication, also middleware has a multicast. For example, if I send information from a data source, then it actually goes for a single copy, as you can see here. So here is a description of what this data service, distributed data service means. So we can have DDS gateways in terms of protection relays, load emulators, generator control, renewable energy, emulators, and so on. And down at the bottom here, you see also power system analysis, smart meters, energy storage management, and also demand side management. So all these things will be connected back and forth to the DDS backbone. As you can see here, DDS back service, you can write codes to be able to translate this data. So the gateway is the bridge between different types and protocol data. So you try to create a way to properly transfer the data in the correct manner. One of the things here would enable us to bridge the standard in industry communication and protocols. For example, NIST has a capability which actually tell you about increased system resiliency by implementing distributed peer-to-peer communication. Okay, and then this is avoid single point failure. We don't want to do that, and so the DDS communication can also be implemented over wired or wireless network. Okay, and you can see here for the different protocols that appear in the communication layer and then in the application layer, and then the DDS can actually be utilized there to create this type of protocols translation. This is an intra-macro grid communication between each one of those. You will see that there is data filtering and routing services that has to happen between microgrid 1 and microgrid 2, because every one of these microgrids have all kinds of communication where you publish the information that you have, and then another user on the microgrid 2 can subscribe to it and then be able to get that information. Okay? And we have developed embedded control agents with publish-subscribe communication. So some of the relays that does not have the ability to do the type of protection that you have, then we developed this pump and wire kind of a circuit that you could use it to update your hardware to do that. And then we built it here with this type of a circuit that essentially with the DDS and the networking with the TCP IP stack and so on. Okay, so we're implementing the data distribution service as infrastructure in our test bed. We have decentralized distribution standards, and we utilize real-time subscribe protocols, and also no message broker. No message brokers or server, which actually avoid the single point failure, which you don't want. Okay, and then also the quality of data service, QoS profiles are very, very important here, and they wanted to optimize for real-time mission-critical applications. So DDS is approach for that. And we want to be able to test the performance. When we do the update rate, is very, very important. So we tried an example of 10,000 messages that were sent with different message rates from 50 to 100 messages per second, and the delay is observed. So based on the type of communication that you use, and then the test was repeated with different message size. It can be from 32 bytes to 62 kilobytes. We did this particular delay, and then the maximum was 1.2 millisecond delay, which would be the maximum 1.4. So in this particular case, the unicast and the multicast actually was actually a bit faster, so we can use that. This is the smart grid modeling and simulation. As you can see, how do we put everything together here in terms of software and hardware? So at the top, the protocol emulation, the interactive interface, all of them go to the DDS backbone through a communication network, whether you go to the cloud, whether you go somewhere else. Then this is the actual physical test bed, where we have all the hardware, and then the simulation system, where you do your power flow, your system protection, you do everything right here. So this is the system. Everything is connected together here through the communication. So very, very similar to what we do in real-time sequence or simulation that we do in the power system. That's pretty similar to that. So this is a schematic. As you can see here, we have the various generators here with the AC side and the DC side, and all these components and converters that are actually needed for the system are connected as one here. We developed also a test bed interface library, which you can do run simulations remotely. So you can develop a solution there, and then you can test it on the hardware. Okay, through a communication network. It has to be through VPN, but you can utilize that in the system. So we use also the real-time publish subscribe, and then we provide the sort of flexible environment to do that. So we have an interface library, which is essentially a Simulink block. You can drag the various components and then connect them, and then you can actually connect to the test bed through a communication to the communication network with VPN, and then you could run the actual generators and run the system and then test your control from a distant site. So for cybersecurity solutions, we have multi-agent classification for cybersecurity, and then we have machine learning for enhanced awareness, energy storage to mitigate denial of service attacks, and then to operate the security in the design of the microgrid. How do we do that? For example, we have a boost message transmission mechanism. For example, if we have one event that goes to the publisher intelligent electronic device, and each message or each event is associated with a status number, a sequence number, a timestamp, a call data 1, and then this moves over the network. The minute it moves over the network, it's open game. Attackers can pick it up, eavesdrop on it, and then get it and then change. So if it goes to the subscribing ID, it goes like that. So everything is fine. Next, if they have another second sequence number, 2, then it's in the publisher IED who's going to send you that information, and then we'll go with that same type of information and status number 2. So if you are able to capture that information and then make status 1 or make it 2 or 2 make it 1 or do whatever, then you can actually create some kind of habit. Okay? But then if we have another event, number 2, then you will have, for example, sequence number 1, and then for data 2, and then this would be also transmitted over the network. So this is actually the back and forth kind of information transfer that goes among the components operating on the power system, and how cyber attackers can actually pick up the data because they eavesdrop on that information and then pick it up. So that is really what this is done. So we have a new field added. So if an attacker can look at the status number and then change it, okay, then of course it's going to be a cyber attack. So whatever can be opened or can be closed, or be closed can be opened, it can be a big problem. So what we did, we developed another technique by adding a happening sequence. So sequence hopping algorithm that we create a handshake between the publisher and the subscribing IDs in the system. So rather than just having the status number or the sequence and so on, what we're going to be doing also is the hopping sequence. In other words, without the hopping sequence, then you don't have the type of security. So this will be added in here. So for hopping sequence to secure push messages, by the way, this is developed in a patent by us, and it will be in update number 6 for IC 61850 standard. So it is recently being done, and then we already published this, and we have a patent. So hopping sequence is added in the process, and then we do it in the message sequence synchronization and monitoring server, which provides the information between the various components of the system. So that will be used to encrypt the connection and the synchronization and exchanging of the initial data. So what happens here is, you can see at the bottom, the IC 61850 or all the relays, for example, all the ABB relays does not have that hopping sequence box. So the hopping sequence box is an added component. This is actually the basis of the patent that we have received on that aspect. So the publisher ID and subscriber IDs, they have to handshake with the hopping sequence so that no attack can happen in this case. So this hopping sequence algorithm needs minimal computation, and it does not affect the communication protocol timing of communication between components. So we have done some test data here on publishing and subscribing. So we have event 1 and response. The difference between the two, it says that IC 61850 standard says that you have to do this between 4 milliseconds. Okay, if this happened between 4 milliseconds, then we measured here, as you can see, it is actually 1.2 milliseconds. So it is quick enough. Okay. For the second one here, when we go from substation to substation, if we are able to create an attack through network sniffer, then we have the difference between the publisher and subscribe here. The difference here was 1.4 milliseconds. So the hopping sequence can be added to existing devices that does not have that communication level, and be added through a pump and a wire. Pump and a wire is a circuit that you add it to the actual relay, and it pumps its capability from the lower level to a higher level, and it can be used with end-to-end delay. So artificial intelligence attack detection and mitigation. So we have actually a limited degree of being able to do that. Then the traditional rule-based systems can be used for this, and then the rule-based systems usually rely on the static stuff. So machine learning systems use anomaly detection, and this means that the model define propositions as normal if an outlier can be detected in that type of system. So we can look. Okay. Online false detection here, we can see. We can identify the anomalies that exist in the lines in between, and then we can identify the difference between fake and moderated data. So the road ahead to AI, we need to output models to identify unknown threats that may appear before they happen, and the multi-agent activities. For example, the idea between the different multi-agents is the multi-agent is looking at the operation of the other agents next to it, and it's actually gossiping and sending and translating the information. Okay? So one more slide, I think. And so this is again the actual multi-agent field agent. Here, what you create the data distribution service here with the different protocols and the agent requirements for interaction. Okay, so this is the agent actually uses ACL, which is the agent communication language, and it's Java activity, and we have implemented that also on a cloud interface. And we can do that with the DDS-based multi-agent type of relationship that you can see here has also been implemented. So this is some of the things that we have been doing, and this is the end of my presentation. You can read. Thank you.